In the last video, we discussed already about the chemical equilibrium in detail, and this is the second part. In this, we are going to discuss about the characteristics of equilibrium and the equilibrium constant, which is very interesting and important topic both for JEE mains and NEET exam. Let's strengthen our basics here, and we are going to discuss the problems, the important models on this chemical equilibrium in the coming videos. Right. The first one, characteristics of chemical equilibrium. Suppose if we consider the chemical equilibrium, we know that it is established in the reversible reaction. If the reaction is reversible, then only we can expect the chemical equilibrium, right? That means, suppose if we consider H2 and I2, the reaction between H2 and I2 in a closed vessel, no doubt H2 and I2 combine together to produce HI, and after some time they establish the equilibrium. Instead of taking H2 comma I2, if we take HI first in the closed vessel, then that time also it start converting into H2 and I2. It decomposes to give H2 and I2, and after some time, no doubt there exists equilibrium between H2 comma I2 in the reaction vessel. That means the equilibrium can be established if in both the direction, regardless of the direction, it can be achieved from both the directions. And we know already the equilibrium is dynamic in nature. Though the concentrations of reactants and the products are constant at equilibrium, we came to know that both forward reaction and backward reaction takes place with to the same extent. Continuously they are taking place. That means the equilibrium is not static in nature, it is continuously in motion. That is what the dynamic nature is. Once again, at equilibrium, in the reaction vessel, as most of the parameters are constant, the reaction appears to be stopped, but it is not the case. Both forward reaction and backward reaction takes place continuously with the same rate, and hence it appears to be stopped, but there is no net change in the parameters, and hence it is not static in nature, the equilibrium. And the third characteristic point is about the catalyst. Suppose if we use a catalyst in the reversible reaction, we know already about the catalyst, which changes the rate of reaction, which increases the rate of the reaction. Here, if we apply or if we add catalyst to a reaction vessel, then it increases both the forward reaction rate and backward reaction rate to the same extent. To the same extent. That means if we consider the catalyst cannot change the state of the equilibrium, cannot change the state of the equilibrium. It does not have any effect on the equilibrium. The equilibrium may be reached quickly. In more or less time, it may reach quickly, but definitely the relative concentrations are remain same in the equilibrium. That we are going to discuss in detail after discussing about that equilibrium constant. Okay, anyhow, we know already about the parameters which are constant, which do not have any change at equilibrium. They are nothing but color, pressure, concentration, density, temperature, refractive index, etc. Right? And let us see some are the other characteristics here. Gives the free energy. In the thermodynamics, we know about the G, delta G. If we consider it is 0 at equilibrium, if the process is at equilibrium, the delta G value is 0, and equilibrium can be affected. We can disturb the equilibrium by means of factors like pressure, volume, concentration, and temperature. Right? Now, suppose if the system is at equilibrium, If we disturb it by adding reactants or by removing the products or by increasing the temperature, etc., it itself moves towards the equilibrium state spontaneously and it will return to the original state again. And that comes under the Le Chatelier's principle, which is a different topic that we are going to discuss. Anyhow, these are some of the characteristic properties of chemical equilibrium. What is the first one? Equilibrium can be attained in both the direction, from both the direction. It is dynamic in nature. And if we consider the catalyst does not show any effect on the equilibrium state, but equilibrium can be attained quickly in more or less time. The equilibrium can be achieved quickly, but relative concentrations of reactants and products are same. And we know already about the constancy of some of the properties like color, pressure, concentration, etc. at equilibrium. And at equilibrium, then the delta G value is 0. And we can disturb the equilibrium by the factors like pressure, volume, concentration, and temperature. And if we disturb the equilibrium, it itself changes its position and it moves towards the equilibrium state spontaneously on its own and will return to the original state that we are going to discuss now. Now, before going to check some of these points in detail, we need to know what is equilibrium constant. For that, we need to understand what is law of mass action. Let us see what is law of mass action. If we consider any reaction, the rate at which the substance reacts always directly proportional to the active mass of the substances. Active mass is nothing but here the molar concentration, or you can say the mass of the substance that is actively participating in the reaction. The true meaning, nothing but the concentration, the molar concentration, which is expressed in terms of moles per liter, is nothing but the active mass. How we can get the number of moles per liter? Number of moles per liter is per liter is nothing but N by V is the formula for the molarity, and number of moles we can calculate by weight by molecular weight into 1 by V, right? So molarity nothing but active mass. Now we are going to use the term active mass instead of the molar concentration. The concentration or the amount of substance which is participating in the reaction. And that active masses or the concentration terms always shown in the square brackets. And at a particular temperature, the rate of a reaction is directly proportional to the active mass, that means concentration of reactants rise to the powers of their stoichiometric coefficients. Now let us see what it is. Once again, this is the law of mass action is nothing but at constant temperature, the rate of a chemical reaction directly proportional to the product of the active masses of the reactants rise to the power of their stoichiometric coefficients. Now, if you check this one, you will understand it better. Suppose if I consider a reaction, AA plus BB gives rise to products. Let us suppose that this reaction is taking place with some velocity or with some rate. That rate, how it depends? How it depends means more the number of moles of A and B, more is the speed. If we take more and more amounts of reactants, the reaction speed is more. That is what the law of mass action is all about. Here, there are coefficients like small a and small b for capital A reactant and the capital B reactant. Now, the rate of reaction directly proportional to the active mass of A raised to the power raised to the power of their stoichiometric coefficient. A coefficient is small a, so raised to A. B coefficient is B, so B raised to the small a. After removing this proportional symbol, if we keep is equal to, definitely we keep a constant that is nothing but K here. And here the K is called the rate constant of the reaction. So, for example, if I consider A plus 2B gives products reaction, A plus B gives A plus 2B gives products a reaction. For this, how the rate depends according to the law of mass action. According to the law of mass action, rate directly proportional to the power A power 1 and B power 2 raised to the stoichiometric coefficients here. And this implies rate is equal to K into A power 1 and B power 2. Rate is equal to K into A into B square. This is the rate equation. And this is the rate equation, and we know that the K is the rate constant. This is all about the law of mass action. Now, suppose if we apply for a reversible reaction, let us see the rate equations for both the forward reaction and backward reaction. Forward reaction rate RF is equal to Kf into A power A. Here the coefficients are A and coefficient is B. If we consider the backward reaction, how backward reaction, for the backward reaction, what are the reactants here? For the backward reaction, the reactants are C, comma D, right? C, comma D. For this backward reaction, reactants are C, comma D, and hence again raise it to their powers small c and small d here. This is the rate of forward reaction, this is the rate of backward reaction. And we already came to know that at equilibrium, the rate of forward reaction is equal to the rate of backward reaction. That means Kf into A power A into B power B is equal to Kb into C power C into D power D. Right? Now, let's take the Kb this side and all these reactant terms the other side. Then what we will get here? Kf by Kb, which are constants, rate constants for the forward and backward. The ratio will give you the equilibrium constant Kc here. So, Kf by Kb, which is the rate constant of forward reaction as well as the backward reaction ratio. If we consider the ratio is nothing but equilibrium constant, which is nothing but products raised to their powers C, C power C, C power C and D power D divided by A power A into B power B. So here the Kf by Kb value will give you the equilibrium constant. Now, if we consider the equilibrium constant capital Kc, all the concentrations we expressed the equilibrium constant in terms of concentrations. We see, for example, if we consider the Kc we have written like C power C into D power D divided by A power A into B power B, right? Now, if we consider these square brackets, these are all said to be concentrations which are at equilibrium, which are expressed in terms of moles per liter. Okay. Suppose if the reaction is in the gaseous state like this, PCl5 gives rise to PCl3 and Cl2. How we can write the Kc for this reaction? PCl3 products by reactants, right? Rise to their powers. Products are PCl3 and Cl2, hence they have written divided by PCl5. Similarly, Kc for this N2 plus 3H gives to NH3. NH3 is the product, So product rises to the power 2, reactant N2 rises to the power 1, reactant H2 rises to the power 3 is the Kc for the reaction. Similarly, you can see the Kc for the third reaction also. This is how to write Kc for a reaction. Okay, now let us move to the equilibrium constant, which is expressed in different manner. So far we expressed the Kc value in terms of molar concentration. That's the reason why we have written Kc, right? There is another constant, another type of equilibrium constant which is called Kp. Here the Kp is called equilibrium constant in terms of partial pressures. What is meant by partial pressure? The pressure exerted by the one of the gas in the gaseous mixture is nothing but the partial pressure that you will understand and that you came to know in the states of matter chapter, right? Anyhow, let's see how to write the Kp value for a particular reaction. Now listen carefully. Instead of concentration terms, we can use even the partial pressures. For example, if all the reactants and products are in the gaseous state, instead of taking the molar concentration of A, we can take the partial pressure of A. How we can get partial pressure? Partial pressure is equal to mole fraction into total pressure capital P. Mole fraction, molarity, normality, and all you already came to know in other chapter, right? The concentration terms. And here capital P is the total pressure. With Dalton's law of partial pressures, if we know, you will come. If you know, you will come. You will understand it better. According to the Dalton, if there is a mixture in the vessel, the individual gases pressures are said to be partial pressures. Let us say there are A comma B comma C and total pressure is PA plus PB plus PC. That is what the pressure exerted by the A, partial pressure of A, B, partial pressure of B, partial pressure of C. Total will give you the total pressure of the mixture. That is what the P total is. Anyhow, come back to this case. Here the PA is nothing but partial pressure of A. We can get by multiplying the total pressure with the mole fraction. So, how to write the equilibrium constant in terms of partial pressure? Just similar to that of the concentrations. First, we need to take the products and we have to raise them to their powers Pc power C, Pd power D divided by reactants Pa power A and Pb power B. And you know, there is a relation between Kp and Kc that is nothing but Kp is equal to Kc into RT power delta N. Here, R is the universal gas constant, T is the absolute temperature, Kp is the equilibrium constant in terms of partial pressure, Kc is the equilibrium constant in terms of concentrations, and delta N is nothing but the total number of molecules of gaseous products minus number of gaseous reactants. By taking an example, you will understand it better. PCl5 gives rise to PCl3 plus Cl2. Now, first of all, let's write the equilibrium constant in terms of concentrations. That will be PCl3 concentration into Cl2 concentration divided by PCl5 concentration. Okay, and what about Kp value here? Kp is nothing but partial pressure of PCl3 and partial pressure of Cl2 divided by partial pressure of PCl5. And what is the relation between these two Kp and Kc? Kp is equal to Kc into RT power delta N. Here delta N is nothing but number of gaseous products minus the number of gaseous products minus number of gaseous reactants. If we consider the products here, there are two products which are gases. So I am writing 2 here minus number of gaseous reactants, only 1 is there, that means 1. So 2 minus 1 nothing but 1. Therefore, for this equation, how Kp and Kc are related? Kp is equal to Kc into RT power 1. Right? Now, H2 plus I2 gives rise to 2HI. Here all are again the gases. All are again the gases. And delta N, if we consider, it is nothing but 2 minus 1 plus 1, 2, nothing but 0. Delta N is equal to 0. That means Kp is equal to Kc into RT power 0. RT power 0 means 1, implies Kp is equal to Kc. And let us consider another equation here. Suppose if I consider N2 of gas plus 3H2 of gas gives rise to 2NH3 of gas. Here delta N is nothing but 2 minus 4, nothing but minus 2, which is less than 0. In that case, what happens to the Kp-Kc relation? Kp is equal to Kc into Rt power minus 2. That means Kc divided by Rt whole square, right? So, by dividing the Kc with some value, we are getting the Kp. What does it mean? Kp less than Kc. In the first example, how the Kp and Kc are related? Check once. In the first example, Kp is equal to Kc into Rt power 1. We are multiplying the Kc with Rt, then only we are getting Kp. That means Kp greater than Kc. So, Kp greater than Kc if delta N is greater than 0, and Kp is equal to Kc if delta N is equal to 0, and Kp is less than Kc if delta N is less than 0. Here it is the conclusion. Delta N is equal to 0, Kp is equal to Kc. If delta N is positive, Kp greater than Kc. If delta N is less than 0, negative, then Kp is less than Kc. Let us see the units of Kc and Kp. Here, Kc units are moles per liter whole to the power of delta N. As we discussed already, delta N is nothing but number of gaseous products minus number of gaseous reactants. And here the Kp units are atmosphere power delta N. Why we are only considering the gaseous products and gaseous reactants while counting the delta N is, suppose if we consider the active mass which is nothing but the molar concentrations of either reactants or products, if we consider active masses of solids and liquids, solids comma liquids taken as a unity, as if there is no much change in the solid concentration or liquid concentration during the reaction, they are considering the active masses as a unity for solids and liquids. That is the reason why we are taking delta N in order to check the units of both Kp and Kc. And here, suppose if we consider important examples like CaO gives rise to CaO plus CO2. See, let's check this one. Important examples. CaCO3 of solid gives rise to CaO of solid plus CO2 of gas. Let's write Kc first. Here, Kc is nothing but the CO2, because the solid concentration is taken as unity, and hence we are going to write only the CO2 concentration. Exceptional cases. Remember, sorry. Remember here for solids and liquids, as the active mass is unity, we have taken only the CO2 concentration or the active mass of CO2 as Kc expression. And what is the Kp expression for this reaction? PCO2. And what about the units? Mole per liter and Kp units are atmospheres. Similarly, if we consider this particular reaction, Kc for this reaction is nothing but NH3 into H2S, because the solid concentration is 1 and hence only the gaseous concentrations we have taken. Similarly, Kp is nothing but the partial pressure of NH3 and partial pressure of H2S. So these two are very important. Exceptional cases, not only these two, if you observe any solids in the particular equilibrium process, remember that we need to take the concentrations as a unity. Suppose if I consider A gives rise to B, let us suppose that the Kc is the equilibrium constant for this reaction. Then how we write? It is nothing but B by A, right? Now I want to know what is the equilibrium constant if I reverse the reaction. B gives rise to A. Let us suppose that the equilibrium constant for this is Kc dash. Kc dash will be A divided by B this time. Then what is the relation between this Kc and Kc dash? Kc dash is nothing but 1 by Kc. Here the conclusion is when we reverse the equation, Kc dash becomes the reciprocal of Kc. That means Kc dash is equal to 1 by Kc. So if we reverse the reaction, we have to take the reciprocal of the equilibrium constant for the equilibrium constant of the new reaction. This is the first case. Now let us see the second case. I am going to consider A gives C, a reaction, A gives H2C. Let us suppose that K1 is the equilibrium constant for this reaction. And let us consider another reaction which is B gives rise to D. And let us say the K2 is the reaction equilibrium constant for this reaction. What is K1? No doubt C by A. What is K2? D by B. Suppose if I want to know the equilibrium constant for A plus B gives rise to C plus D, in order to get the required equation, if they ask us to calculate the equilibrium constant for a particular equation, which is nothing but a required equation, how we can get from the given equations, we need to check. Let us suppose that this is the first equation and this is the second equation. Suppose if we add these two, 1 plus 2, then definitely we get the required equation, right? Now, what is Kc for this reaction? C into D divided by A into B. That means if we just multiply these two, you will get this expression or not. That is nothing but K1 into K2. So, again the conclusion is if we add the reactions, new equilibrium constant Kc is equal to the product of the individual reaction equilibrium constants K1 and K2. So, equations, if we add equilibrium constant, we need to multiply to get the new equilibrium constant. Here Kc is equal to K1 into K2. Now, I am going to consider the third case now. Third case, let us suppose that for this reaction, Kc is the equilibrium constant. If I take Na gives rise to n moles of B, then what is the Kc dash for this reaction? What we have done here, we have just multiplied the equation with some integer or with some number n here. And what is Kc for this reaction? B by A. Active masses are molar concentrations of B by A. And what is Kc dash for this reaction? B power n divided by A power n. That means you will get B by A is nothing but Kc, Kc to the power n or not. So conclusion here is if we multiply, just bear with my handwriting as it is new to me, I'm not able to write properly. If we multiply the equation with n, new Kc dash or new equilibrium constant will be the Kc power n. Let us consider an example, then you will understand it better. Let us suppose that H2 plus I2 gives rise to 2HI. For this reaction, Kc is let us say 49. Then, if they ask us to calculate what is the Kc value for half H2 plus half I2, half I2 gives rise to Hi, then what is the Kc dash if they ask? What we have done here? We have just multiplied the equation 1 with 1 by 2. That means here n is equal to 1 by 2. To get the Kc dash, what we need to do? We need to take Kc power n. That is equal to 49 power 1 by 2. 49 power 1 by 2 means 14 square root 49, nothing but 7. This is how to apply the rules, or you can say the formulae of equilibrium constant. All the three are very, very important. If we just reverse the equation, we have to take the reciprocal of equilibrium constant. If we add two equations, we have to take the product of the equilibrium constants. If we multiply an equation with a number, then we have to take that number as a power of the old equilibrium constant for the new equilibrium constant. Let us see the conclusions here. If a chemical reaction is taking place in more than one step, then the overall reaction equilibrium constant is the product of equilibrium constant of individual reactions. That is what we discussed. See here. Suppose A gives B, K1, B gives C, K2. Then A gives C means how we can get A gives C? Just by adding these two. That means we have to multiply the K1 and the K2. Understand? Now, suppose if we take the reactions like this. P gives R plus C, A plus B gives C. If I want to know A plus B plus R gives P, then what we need to take here, let us suppose that it is nothing but K3, and how we are getting this um, K3 here, see, suppose if we consider the first equation, in the first equation P is on the left hand side, but in the required equation P is on the right hand side. That means we have to reverse the equation 1. So, required equation we get by adding 2 plus reverse of 1, right? Plus means we need to multiply the equilibrium constants. For the reaction 2, what is equilibrium constant? K2. For reverse one, what is the equilibrium constant? For one it is K1, for reverse one it is 1 by K1. As the equations are added, you have to take the multiplication or the product of equilibrium constants. That means you will get K2 by K1 here for this reaction. Understand? And similarly, when the equilibrium constant K1, if the reaction is multiplied by the factor n, then it comes as a K1 power n, right? So this is all about the relation between the equilibrium constant and the stoichiometry of the reaction. This is how the Kc value depends upon the stoichiometry of reactions, which are very, very useful uh, in order to solve some of the problems. Okay, let me give one example here. O2 plus half O2 gives rise to SO3. For this reaction, the equilibrium constant is K1, and they are asking what is Kc value for 2SO3 gives rise to 2SO2 plus O2. So this is the required equation, right? This is the required equation. In the required equation, where is SO3? On the left hand side. In the given equation, it is on the right hand side. That means definitely we need to reverse the reaction 1. So first I am going to reverse the reaction 1. That means I have to take, if I reverse equation 1, it will become 1 by K1. But SO3, if we consider it has the coefficient 2. That means after reversing the reaction, we have to multiply the equation with the 2. Multiplying the equation with the 2 means multiplying with the 2 implies we have to take 1 by K1 power 2, right? So then the Kc will be 1 by K1 square. This is how to do the problems. That is all for today. Thanks for watching the video. If you really like the video, please try to comment and share the video. Thank you.